now we've done our profiling using PVRTune, I'm now going to move on to using PVRTrace to actually analyze the application itself. So to take a trace, first we're going to go back into PVR Hub, and you can see the PVR Hub is still in the PVRTune recording mode. So all I need to do is click Stop PVRTune Profile. Now to correctly record applications, we need to make sure that they actually are restarted from the beginning. So what I'm going to do is close the water demo, come back into PVR Hub, and now if I click Start PVRTrace Record, all I need to do is pick what application I want to record. In this case, I'm going to choose the water demo. So all the API calls that this application is making are now being recorded by the device. One thing to bear in mind when you're taking trace recordings is that it adds a lot of workload to the device. It's saving every single API call and textures and memory associated with those API calls to a file on the system. These files can quickly become extremely big, especially if there's a lot of new assets or textures every single frame. Okay, so to stop the recording, I simply close the application, and if I go back into PVR Hub, you'll see that it's now not doing the trace recording anymore. So one thing I can do, if I go into File Manager, I can see that that trace I just took was about 50 megabytes, and I can now copy that off the device using ADB. Okay, so if I open up an ADB shell, and if I go into the following directory, you'll need to be root to do this. Okay, so if I go into this folder, /data.com.powervr.pvrhub/files/rec, you'll see that the trace is in this folder. Now, with the utility, we can also copy this into the SD card location. And this just helps if we don't have root access, because then we can copy it from SD card. But in this case we do have root access, so we'll just copy it from this path. Then all I need to do is ADB pull and select that path. So that is now copying over to this machine. And at this point I'm actually finished using the V989 tablet. Okay, so now that we've taken the trace file, all we need to do is open it in PVRTrace GUI. So we open the application and simply open the file. So when you initially look at Trace, it's quite a busy application. There's lots of panels all around, so I'll quickly try and explain each of these panels in depth. So the middle panel is the actual API call stream. These are all the EGL and GL calls that were recorded by the Trace utility, and both the function parameters and also the return values that came back from them. You can see that in the first frame there's a huge amount of setup. There's lots of get proc address, texture uploads before we finally begin rendering the actual frame. You can see these draw calls highlighted here. And then to actually get around all the different frames we recorded, in the bottom right we can see the current frame we're looking at, frame 0, and how many frames are in the trace. So one of the first things you might want to do is actually pick what frame is important. And so let's say in a normal game there might be a loading screen and then the actual game content comes a lot later. In that case we can use Tools Statistics Graph to get an idea where that occurs and go straight to that frame. As this is a simple demo, the function calls are pretty much the same throughout the entire trace, But we could imagine that as time goes on, this first part might be a loading screen, then a few warm-up phases with lots of texture upload calls, and then finally we might settle into the main game scene. So let's kind of follow that idea and let's go from frame 371. Additionally, if you had an application that was using multiple threads, you could look in the thread usage graph, and this will let you know where those thread interactions are happening and on what frames. You can see there's a whole host of useful things we graph in this statistics view, things like shader compilation, texture uploads in particular you might see in the warm-up phase, and then finally like general triangle count and draw call counts. Okay, so once we've actually chosen our frame to analyze, one of the first things we'd tend to always look at is this static analysis view. This is actually for all the frames, and what it tells you is kind of it's based on our performance recommendations, and it will give you warnings about certain things you're doing that might be costing performance. So for example, here we've got 6 uses of uncompressed textures. Now in this case they're probably for texture, they're probably for drawing text, things like fonts or UI elements. In that case it's fine, but it's just to alert you, that at this frame we can simply click on it, we can have a look, we've uploaded a texture, and is this something we intended to do? Maybe we did it by mistake and we did intend to use compressed textures. Generally this view is very useful to just finding things that maybe you didn't realize you'd done. And then we have kind of a warning system that goes from level 3, which is kind of just an advisory, to when we get to things that are kind of warning level 1, these are calls that are going to be particularly expensive on the hardware and are actually going to cost you a lot of performance. This might be things like GL read pixels or accessing buffers in the middle of draw calls and things like that. Okay, so when we come into Trace, we've generally first been looking in Tune and we have an idea of the kind of issue we're looking at. So let's start from the GLES to water demo and assume that we actually found that we were vertex processing limited. We were simply submitting too many triangles and we need to look for points in our application to reduce the amount of triangles that we're submitting. Let me reset this back to a normal game frame. Okay, so at this point we could look inside the statistics tab. So here we've both got a call summary and a frame summary. So if we go into frame summary, we can see how many triangles are being drawn in this frame, how many draw calls and how many function calls. In this case we can see it's about 80,000 triangles, which it's a very light workload. But if we saw this in the kind of in the millions, like over 1 million triangles, that's where we can start to look at this number and think, okay, this is the issue, we need to get this triangle count down. Equally as we go, I'll try and talk about also the CPU, if we're CPU loaded. When you're looking at CPU loaded trace, you might find that these function call and draw call numbers are extremely high, in which case to kind of improve performance you need to come up with ways to remove redundant function calls or redundant draw calls or try and batch draw calls together. So say you were CPU loaded, this call summary view is then very useful because it's showing us how many times each function was called in this frame, and then we can quickly see if there's maybe it's like a redundant call. Maybe some of these enable disable vertex array calls, some of them aren't actually needed or aren't actually affecting the render state. Okay, so once we've decided that it's the actual geometry, we can then come down to this draw call view. So this is for every single draw call in this frame. It tells us the type, so elements, or and then finally how many vertices are in that draw call. So all I'm doing here is ordering the draw call by vertices, and at the bottom we can see we've got these really quite expensive draw calls towards that seem to repeat, and this makes sense when we think about the application. We know that it's going to draw this scene for above, below the water, and then a final pass where it draws the actual final scene to the frame buffer. So we can expect to see all this geometry coming in 3 times. So we might be interested in say, okay, what is this piece of geometry that it's taking 31,000 triangles? So with Trace, what we can do is see that this is, say, draw call 7. And if we go into image analysis, this is actually rendering what was recorded onto the device on this laptop's graphics card. So if I expand this out a little bit, at the moment it's set to normal, but the first thing we can do just to get an idea of the whole scene is switch to wireframe, and now we can see what triangles actually comprise this scene. We can see immediately that there are a lot of triangles here. This is a very triangle dense part of the scene. Now if we actually want to see single draw calls, we can use a mode called single primitive. So at the moment what this is showing us is every draw call from 0 to 41. We can choose any arbitrary range. We could look at just draw call 0 to 1 and it will render draw call 0 to 1 as we see them. But in this case we want to see exactly what draw call 7 is doing. So all we need to do is select single primitive and go to draw call 7. Okay, so all we need to do is select draw call 7, and here you can see it's rendered the wireframe that was responsible for all those draw calls. Now you can see basically this will have gone through a lot of culling because it's drawing below the surface of the water. But we can quickly see, that okay, this was an expensive piece of geometry to submit, in the sense that a lot of what was processed was just immediately thrown away by the hardware. Again, we can look at this just in a normal view to see what actually got shaded as part of the output. And again, you can see that it's smaller than the actual render resolution, so we're most likely rendering into an FBO at the moment. So just generally, this view can be used to understand what's actually happening in the render. If we continue clicking through the draw calls, we can see what effect each draw call is having in the scene, and go through the entire demo this way. So here we can see the kind of the top reflection of the water is fully rendered now, and we can understand what draw calls made up and comprise this. Within this we can also look at any particular FBO. So at the moment the scrubber is following whatever draw surface is currently bound and showing us the draws to that, but we can select just say FBO 1 and look at each draw call to that FBO in turn. Okay, so let's now look at the case in which we're fragment bound. So I'm going to return this to looking at the entire scene again. Okay, so here we've got the scene as we saw before, and all I'm going to do is, for the beginning of this process, is click on the shader analysis tab in this object data view. Now what's happening now is that it's using our offline compilers and the estimated cycle counts for any given fragment shader to calculate the cost of every single different shader that was run on this scene, how many times the shader had to be run, and then multiplying that by the emulated cycles. So we get quite an in-depth analysis of what was the most expensive shader to run and how many pixels did it shade. So all we need to do is say look at this pie chart, and we can see that shader ID 26, so this is currently set to fragment shaders, was used to shade 1.5 million pixels on the screen, and there's 5 texture reads, it's taking 34 cycles. From here we can basically just double click on this shader and we're taken straight into the source code of that fragment shader. Once we're in this view we can see firstly a line by line cycle count. So here we can see this is taking 12 cycles to process, and we can actually also change these shaders and check the effect. This is quite useful because we can firstly use this to optimize our shader, but secondly we can also live see what the cycle count's going to be, and maybe we're sacrificing some visual quality to reduce the cycle count, but we can click apply and immediately see the effect. So for example, I can change this frag color output to just output pure white. And then if I click apply, it will re-render the scene with my change to that shader. And you can see now this shader now takes 1 cycle to execute. And we can see that firstly, by doing that, we now know that it was the water effect that was the most expensive shader in this scene, and you can tell that by just visually checking the scene, and now that entire part of the screen has gone white. So this helped us quickly identify what the most expensive shader was, and maybe we could do some work to optimize that. But if the shader is already optimal, we might need to look into certain other issues. So what can happen quite a lot is if a scene is so-called overdrawn, maybe there's a lot of blending going on in places that isn't necessary. So let me actually revert this change to the shader. And we're now going to use another mode of image analysis. So if we use PowerVR depth complexity, what this is going to do is process the scene in terms of how our rasterizer sees it and how it performs so-called hidden surface removal. This really reduces the amount of pixels that needs to be shaded by being completely order independent for opaque objects. And when we're in the PowerVR depth complexity, you can see that the only things that have been overdrawn or need to be blended are the actual text and logos in the top left and bottom right of the screen. Now, we can imagine that in some applications we might not be as lucky as this. Where this is black, we basically just shaded 1 pixel. It was 1 pixel in, 1 pixel out. And up here where it's blended, you can see there must be, as it tends towards white, it means more and more layers are blended. So here we've got 2 pixels being shaded, and here we've got 3 pixels being shaded where 2 text characters were overlapping. Now you can imagine kind of a demo where maybe we didn't anticipate there was going to be as much blending, and in that case this depth complexity view is very useful. We might see that actually a particular usage of the API meant that an entire blended extra piece of geometry was over the entire screen. And then we can kind of quickly try and figure that out by, if we use this thing called the pixel picker, wherever we click, here we're shown what fragment shaders were run for that particular portion of the screen. So I can see that fragment shader ID 4 and 40 were run to draw this part of the screen, and here we've got 12 and 37, and here we've just got fragment shader 12. So this helps us very quickly, we can identify in the source, what are the causes, what draw calls caused the blending to occur. So once we've got an idea that there's some extra blending occurring, we can then use the state inspector to get an idea of, when is this blending actually switched on. So I'm going to put this back to normal. And then return to just the object data viewer. So if we start looking at the scene going through the draw calls, we can use what's called the kind of state inspector down here to understand when blending is switched on and off. So if we start with, say, draw call 1 and then click this option, hide and changing state, this will remove any state inside the GL state machine or EGL state machine that hasn't been changed by this GL application, so it's just been left at default. So if I click hide and changing state, I can immediately see, okay, I've got program 32 bound, and I can see what textures are bound in my different texture units. I can see what frame buffers are currently bound, and importantly down here I can see the current blend state. And as I continue to go down this list, I can see this changing as I'm coming through. And then finally on this call 40, I can see that blending has been enabled, and because it's highlighted in red, it means it's changed since the last draw call. So again, this object inspector lets us very quickly figure out when was blending switched on, when isn't it switched on. We also have an EGL object inspector, so it's very easy to tell, say, if we've got something like multi-sample anti-aliasing enabled, we can just look for the EGL samples call, the EGL samples configuration. And then we also have just a general objects view. This is all the objects that are being uploaded by this trace. So every single texture, all the shaders that have been uploaded and compiled, the frame buffer objects, render buffers, and also just generic buffers. So from here we can actually inspect buffers. So say we can, for any attachment to a frame buffer object, we can look at what's currently inside the color attachment, and we can even view the depth texture. So here we can see the depth attachment for one of the FBOs, and also its width and height. So from here we can see that the FBOs are rendering at 1024 by 1024, but the actual main render was at 2048 by 1440. So again, if we were finding that we were kind of texture bound, we can also use this to very quickly check, what are the actual dimensions of these textures? Are they compressed? So in this case we can say these are all PVRTC version 1 textures at 4 bits per pixel. This seems like quite a sensible resolution. It's correctly mip-mapped. Basically just use this object inspector to very quickly verify that textures are in the formats we expect and in the sizes that we expected. Okay, so that was a quick summary of how to look at issues where we're bound by fragment processing. So now I'm just going to go through the kind of general features for actually understanding the main call stream. When we're looking at cases where maybe when we looked at PVR Tune, there were lots of gaps between the blocks, or it looked like we were blocking on the CPU, so maybe the GPU is waiting for the CPU and then the CPU waited for the GPU. That's when we want to really start using these kind of filter and searching features. So first thing I would start to look at that point is come into this filter view. And then, maybe there's a particular call we're looking for that we know is going to be an issue, or we're worried about how many calls there are to it. So what I might tend to do is say like hide nearly all the API calls and then just look for specific things. So maybe the order in which we're binding and switching between frame buffers is causing problems, or kicking more tasks than we'd like. And then I'm still going to keep displaying and highlighting the draw calls. So if I just click accept, you can see now everything has gone grayed out except for the calls I'm particularly interested in, so these bind frame buffer calls. And then all I need to do is just click the filter, and I'm just given a very simple view where all we can see is the draw calls and the GL bind frame buffer calls that I was interested in. Okay, so if I remove these filters again, we can also do this from within the UI, so I can say add filter. These are now all grayed out, and maybe I'm interested in which textures are getting bound, so I can just say add highlight, and again if I just click the filter we can quickly get a better understanding of this trace just by visual cues. And again, another very useful feature that's implemented is within these traces we fully support a regex search engine. So maybe I'm looking for when a particular texture was bound. So let's say I'm looking for texture 16. If I just open up a search dialog, I can look in the current frame and select regular expression, and I know that I'm looking for something like GL, bind texture, and then I'm expecting a value of 16 somewhere. So we've got found one element, and here we can see the bind texture call of 16. So it's it's got a very powerful filter and searching engine, and this really can you can very quickly find cases of maybe API calls that you need to avoid. Typical things like read pixels, or maybe binding a frame buffer and then binding back to it again within the same frame. These are all things that can cost time on the hardware, and I really hope you can see that this tool can help you very, very quickly identify those issues. One feature of Trace that is often missed is the remote recording. So what remote recording lets you do is, say you've got a game scene and there's a kind of a big intro sequence, like a video plays and you have a menu, and you don't want that to be part of your trace. From PVR Hub, if you select a network recording, then you can pick when to actually start the trace. So you basically start your device, connect to it locally. So if you're using ADB, then you need to forward the network recording port. And then you simply click go, and when you get into the main game scene, all you need to do is click start recording, and then you will only capture a trace from that frame onwards, and that will then download straight to Trace GUI through this UI. And the last feature I'd like to talk about is, say you're having real trouble doing performance analysis, and we always offer free support through either our support forums or ticketing system. And if you do want to provide a trace, and maybe the trace file is absolutely huge, a few gigabytes, what you can do is, if you come into the UI, you can choose save as, and then just pick a range. So you could say, actually, I only want to send from frame 1 to 2. And then this will save out a much smaller trace that is just those single 2 frames, and then you can send that to us much more easily. So hopefully you've got a good understanding now of how to use PVRTune and PVRTrace to profile your applications. If you have any further questions or want a hand using our tools to profile or analyze, then please post any questions to our forum, or otherwise you can send us a support ticket on pvrsupport.imgtech.com. This is our confidential ticketing service, and if you have maybe an application that you don't want to share publicly, then you can send traces through this and ask us for any advice on any performance issues you might be having.